Hi everyone, and welcome to this video. Today we are going to discuss performance metrics of classification, and it's all about how do we evaluate models that we build in classification problems. In a previous video, we were able to discuss the type of machine learning techniques, including supervised and reinforcement learning. And under supervised learning, we were able to see that there are two types of supervised learning approaches: regression and classification. In regression, we were able to discuss also linear regression, where we built a model and evaluated our linear regression model using metrics such as the R-squared, which tells us the percentage of the independent, the percentage of the dependent variable, the percentage of variation in the dependent variable being explained by the independent variables. We also saw other metrics such as the root mean squared error, the mean squared error, AIC, and BIC. So for classifications, we strive to assign an element into a class or a group, which is either binary or multiclass. And some of the ways we'll be able to evaluate models built for classification problems is the use of metrics such as the accuracy, precision, recall, F1 score, area under the curve, the ROC curve, and also a very important tool that will be used to computing almost all of these metrics is the confusion matrix. So we start off with the confusion matrix, and the confusion matrix is just a side-by-side table that compares the observations and that are actual compared to the predicted. So in this instance here, we are having a binary situation, a 1 and 0 classification, where we are able to see a model predicts true and the observations were true. So this is what we call the true positive. For example, model predicts a patient has diabetes, and they actually do. We also have false negative, and here these are the observations that are predicted to be negative but are actually positive. On the other side, we have those which are actually negative but have been predicted to be positive. We call them the false positives. And also those that are negative and have been predicted to be negative, we call them the true negative. So from the previous confusion matrix, maybe some of the terminologies that may be familiar, the false positive and the false negative. And this is what we call, for the false positive is what we call the type 1 error, or the alpha, and it's just the predicting a positive outcome when it's actually negative. And on the other hand, false negative, it's the type 2 error, which we call the beta. So onto our first metric is the accuracy, and accuracy is the proportion of correct predictions made by the model. So our correct predictions are the true positive and the true negative, and we're going to have them as our numerator, and then the total observations as the denominator, which will include the false negative and the false positive. Accuracy is a good measure when the target variable or the data in the class are nearly balanced, for example 60 to 40%, and therefore this means that the model, when this data is used, even without a lot of data preparation, this model can be able to, at least it won't be biased, and therefore accuracy will be a good measure. It's also not good when now the inverse is true, where we are having more class being present rather than the other one. The second metric is the precision, and precision is the proportion of correctly predicted positive cases out of all the cases that are positive, predicted to be positive. So here we have the numerator, the true positive, divided by the true positive plus the false positive. And we use precision when false positive are costly or harmful, and you want to minimize the number of incorrect positive predictions. For example, here when you are having email spam detection, you don't want important emails wrongly marked as spam, and therefore that's how precision may be of more concern in that instance. In short, precision is just how correct are your positive predictions. On the other hand, we have recall, also known as sensitivity, and this is now, out of those, what is the proportion of correctly predicted positive out of cases that are actually positive. So remember, the actual positive are the true positive and the false negative, but now we have the true positive as our numerator divided by the sum of the true positive and false negative. So we use it when false negative are more dangerous or more costly, and we may want to minimize this. For example, in disease screening, where missing a patient with a disease is more dangerous than testing healthy people. Really, imagine you are telling you are diagnosing a patient and telling them that they are negative, yet they're actually positive, and maybe they may it's a communicable disease. So therefore, it will be really important to minimize the false negative. Now, the last metric that we have here is the F1 score, and this is the harmonic mean of the precision and recall. So it's a single metric that balances both the false positive and the false negative, and therefore this is the mostly used metric. And a couple of interview questions usually asks about this, and you'll see machine learning guys just trying to ensure that they have higher F1 scores or higher values of the F1. So we compute F1 by saying 2 multiplied by, our numerator will be the product of precision and recall, and our denominator will be the sum of precision and recall. So we have an example. Here. Just try and implement what we've seen. So we have a data set with 268 total cases. Out of this, 111 are positive and 157 are negative cases. Our model was able to predict 120 positive cases, out of which 108 are actual positive and 12 are from actual negative cases. So we are required to create a confusion matrix for the task and compute the model accuracy, precision, recall, and F1 score. You can pause the video to try and attempt this, then come back and see whether and compare our output to what you have. So this is the confusion matrix that we have here. So from the statement, we have 108 which are actual positive. We have a total of predictions of 120 as positive, but 108 are actual positive. So the model has correctly predicted as positive, and they're actually positive. So these are our true positive. So we'll assign here true positive 108. But we also have 12 that are from actual negative cases but have been predicted to be positive. So these are our false. These are our false positive. So we'll put it here. They have been predicted as positive, but they are actually negative. So remember, overall we had 111 positive. So we just come and say 111 minus 108. We get our false negative. Then we also have 157 minus 12, and we get our true negative. So quickly computing the metrics, we'll be able to see that our accuracy will be 94.4%. After computing this 108 plus 145 divided by 268, you'll get 0.944. You can easily just convert into a percentage. Also our precision which just sees of the positives that have been predicted to be positive, how many are the true positives. So we see 108 divided by 120, which is 90%. Our recall is 97%, and our F1 score is 93.6%, which is a very fairly high number. Lastly, we are going to see, although we don't have an example for this, but we'll be seeing later in our programming tasks in the videos to come, we have the ROC curve, which is just, it plots the true positive rate, which is recall, versus the false positive rate. And the false positive rate is just computed by FP divided by FP plus TN. And then when we now see our curve, when we plot our curve and just try to measure the area that has been covered by this ROC curve, which we call area under the curve, we'll get our area under the curve metric. So of course we want our graph to cover a higher area. So the higher AUC, the better it is. And this is what we want. I will be seeing this. This is similar to how we find the area under the curve in integration, where we just want to see how much area has been covered by the curve. So there we have it, guys. We've been able to discuss the classification metrics, performance metrics for classification. We'll be seeing a couple of these in the subsequent videos, including one which is coming recently on logistic regression, on how we'll be able to implement each of these in R and Python. If you enjoyed this video, give it a thumbs up, and ensure to subscribe and share so that we may be able to learn more together. Thank you, and I'll see you in the next one.